non-standard states. This would be where you're using Q for the reaction quotients instead of the equilibrium numbers for the K, for the numbers that go into the equilibrium expression. But basically what always comes out is delta G negative. And remember, that doesn't read less than 0 in chemistry. It may read less than 0 in math class, but in chemistry it just reads delta G is negative. These are spontaneous. And if it's positive, it's not spontaneous. And remember, if you swap the reaction over, interchange the reactants and products, what does it do to the sign of delta G?
Opposite.
Makes it opposite, right? So if the reaction is spontaneous, the reverse reaction must be non-spontaneous. It's the same thing. If in one direction the reaction gives off heat and it's exothermic, if you write it in the opposite direction, it's going to absorb heat and be endothermic. That's why I say signs are important, because when I give you different versions of quizzes, that's basically one of the major things I do is reverse the equation. And then if it goes from spontaneous to non-spontaneous, the criteria that you need. And when the reaction is at equilibrium, remember, it's not going in one direction or the other. There's some reactions that are going in the forward direction in the container, and somewhere else in the container there's some of the things that are reacting and going in the reverse direction. That's what it means when they say dynamic equilibrium. And the key result of this was that and I talked about thermodynamic equilibrium constants, but we don't really have to worry about that too much because we didn't do any calculations with those mixed phase reactions. We said they exist, you can write the equilibrium expressions for it, but when you have something like the activity of the calcium ion and the pressure of the CO2 gas and everything, those were not any of the problems we actually dealt with. We worked with case of A's, case of B's, and things like that. And those, what you come out of here is going to be exactly what you have been working with. So we don't really have to worry too much about it, except to recognize that some of the shortcuts we take are not necessarily shortcuts, the things we do. For instance, this thing right here. If you were to calculate delta G for that reaction, you have to look this up in the table of delta free energies of formation for ions. You have to look this up. That means you have to put in the free energy of formation for the H2O liquid. And you also have to put in the free energy of formation for the weak acid. So that's why it's a thermodynamic equilibrium constant, because you put in all these free energy changes to calculate it by sum of products minus reactants, you get this number. That means the equilibrium constant theoretically has this in it. But when we did equilibrium, we didn't put this into our equilibrium expressions. And I said some weird thing like the concentration or the activity of the water is mixed into the case of A number, which sort of works around this a little bit. Okay. But we didn't have to worry about it, we just did the problems with it. So anyhow, here's the relationship that takes you between delta G0 and the equilibrium constant. Let me just say what I'm going to do here before this guy goes off. Let's see. But basically, I'm going to get through the temperature effects, and I'm going to start the introduction to the electrochemical cell. Supposedly, today as part of the lecture, I'm supposed to talk about electrode potential. Electrode potential, I probably won't. I'll save that for the next time. But now what happens is, and we saw that table, we saw the table if delta H is negative and delta S is positive. You can get reactions that are spontaneous at one set of temperature and non-spontaneous at another. In other words, they can change the signs. If they're both positive or both negative, you have different effects with the temperature. here we're going to do the calculations. And suppose what I always give you because that's the data. I'm not going around. If I were teaching a course in thermodynamics, we'd have a detailed set of equations that allow you to calculate delta G zeros at every temperature. It's a big, long expression, and it has about 3 constants, and you put in the different temperatures, and you have squared factors or whatever it's called, a variable expansion. So in a big table, they don't have the things you have in the back of the book where they just write numbers. They have an equation for calculating delta G. You can calculate delta G zero at any temperature. Okay. So for convenience in the book, they just give you most of the data at 298. And the other reason they do that, of course, is a long time ago when you did thermodynamics, you worked at room temperature, which is about 25 degrees. I don't know why, but that's the temperature they said planets were. And so a lot of data was accumulated and measured by working around 25 degrees Celsius. So that's another rationalization for doing. So we always get data for delta G at 298. Now suppose I wanted to calculate, and this would give you the equilibrium constant at 298, and that's the number that would go in here. Suppose I'm going to calculate K at 450 kelvin. What do I do? Well, if this were a real course in thermodynamics, I'd run to the handbook, I'd pull out my big equation, and I'd calculate delta G at 450 kelvins, and then I'd plug that number in here, put in the 450, and I'd get K at that temperature. But we're going to make an assumption here that allows us to do that, and that is the fact that they don't change much as you change the temperature. They do, but not by much. So we ignore it. And the easiest way to think about that if I take a mole of liquid water and convert it to a mole of gaseous water, there's a certain entropy change because what I'm doing is breaking these molecules that are close together and pulling them far apart, and you get a lot of randomness when we convert it to the gas phase. And it doesn't matter whether I do that change at 298, whether I do it at 300, the degree of randomness that you get, in other words, the entropy of this goes up as the temperature goes up, the entropy of this goes up as the temperature goes up. But the entropy change between these two states stays essentially the same as the temperature increases. And as I said, that's not exactly correct, but for the purposes of this textbook and beginning chemistry classes, that's the assumption. And the same thing happens for delta H, although that is more sensitive to increases in temperature or changes. It doesn't matter whether it's an increase or a decrease. So delta H is more sensitive, but again, most of the things we do assume that that doesn't change with temperature. So that's a hidden assumption. That underlies everything you want to do. So that means, let me pick a reaction calculation. I'll do delta H sub F. The reason I think this is because you already remember, that's kilojoules per mole. Okay? So I remembered that, that's another reason I picked it. Now, this is correct, this is the number at 298. In other words, 25 degrees plus 272.15. But But what we're gonna do is assume that this is the same number at higher temperatures or lower temperatures. Okay. Also, I can calculate delta S0 for that reaction. And now I need to look at the data because obviously I have to do a calculation. So here's CO2, and I'm going to work with the gas. And this, by the way, is a mistake sometimes people do because they see S0 for CO2. Just forgot it already. S0 is 213.7. So they say delta S0 for the reaction is 213.7, but it's not. The reason this is the delta H for the reaction is also the delta H sub F is these things were defined as 0. So whatever we measure for this reaction gives you delta H. But this, since we're working at 298, all of these have positive numbers for the entropy. So when I want delta S for this reaction here, I have to take the products minus the reactants. So I look up oxygen, 205.0, and carbon is here. And I'm going to use standard state because that number was the standard state number. So carbon, graphite, 5.74. And by the way, when I give you these numbers in the tables, you may remember something else because you used a lot of them. Use the numbers I give you because, again, I make small changes so that people can't just say, I remember that, and write down the answer. You have to calculate it. Okay, so I expect to see those small changes appear in your calculation. Not that they're as accurate as they could be, but I put that in just for test giving purposes. So here I would have to say delta S is going to be minus, can't read my writing, I think I said 5.74. 5.74. And minus, and notice it's going to be slightly positive. Now if you look at this, solid, gas, gas, you can't make an estimate because these are both gases. We know that you have 1 mole of gas on each side, and you have a little bit of solid, but you don't know if the entropy for this outweighs the entropy for this. You actually have to do the calculation. For this reaction, you know right away there's a lot more, the entropy on this side is much higher because gases are more randomized than liquids. Yes?
So when you determine more randomness, it's based on the gases, it's not based on solids?
No. This is a solid. When you're doing that rough estimation, yes, because you can't. What we always say is, if you had a reaction where they're all solids going to solids, you can't estimate the entropy change.
Okay.
If you have solids going to gases, solids going to liquids, you can always say liquids have higher entropies than solids, gases have higher entropies than liquids, and so you can make an approximate guess as to whether you have an entropy increase or not in the reaction. But if they're all solids, you can't figure that out. If they're all...
Because I saw that there's 2 moles on the right side and 1 mole on the, 2 moles on the left side and 1 mole on the right side.
If I have a reaction where I have 2 moles of molecule A, which is a gas, and 1 mole of molecule B, which is a gas, and it produces 3 moles of molecule C, which is also a gas, you can't use that rough rule because you have 3 moles of gas on each side. The only way you can decide whether the entropy increases or decreases is not by doing a calculation like this. But if I have a liquid on one side and a gas on the other, you know, this is a higher entropy
Yes.
state, lower entropy state, that means delta S for this reaction is gonna be a positive number. Okay? So that's all that is. You're looking at the different phases to estimate which has more gases, that's the most important thing. Or if there's solids and liquids, which side has more liquids and fewer solids. If it's all solids, the only way you can do it is go to the table and get numbers. Or in this case, same number of moles of gas, but this has a solid, but you still can't decide because different gases, this is more complex than this, so it would have a higher entropy state than this. So you can't decide, but when you go to do this calculation, now you're gonna see it's a positive number. And whenever you do the calculation, that's the ideal state. That's what you would like to do. Get that number. Anybody that wants to use one of these, you have to go to the screen, you erase the memory, bring it up and show it to me before you get to use it. I do have regular calculators that have the same functionality that you can borrow for the exam. I'm still trying to decide what to do with the ACS exam. That's on the final exam. Where it says no programmable calculators, and I always make the joke, they say that because they don't want students storing all the answers for 10 of the questions, and somebody else stores all the answers for 10 of the questions, and then they go out and sell it to somebody so that somebody else can pass the exam. The ACS worries about that, because people are desperate to get into medical school or get an A in chemistry. The schools use that, I use it, so the ACS is of the opinion people are going to get out there and somehow cheat, and they're going to store numbers in their things and say question A has the answer, or question 1 has the selection A, and question 2 has the selection A, and question 3 has B. And so you store 10 of them, and you take it out, your buddy stored 10, and pretty soon you have all the answers for the exam. And then you sell it to somebody that's got multi-million dollars but not bright enough to pass the chemistry test, and they want to be a doctor. People wouldn't do that. I don't know. But the ACS worries about things like that. So coming back to this thing, what was I doing? Oh, I was talking about, if you're going to use this, for our exams I don't care, because you can store a lot of stuff and I can just change 1 or 2 things, and either you have to know what you're doing to use it or you don't. But when you have a multiple choice question, the exams don't change the multiple choice answers from year to year. Oh, what's the joke in, I forget, it's not history, in psychology. You can give the same multiple choice exams every year, you just change the answers. There's some course they make that joke a lot. You can't do that in science. I forget what course it is. There is some course where the joke is, I give the same exams every year, I just change the answers. Or the same questions with different answers. Okay, coming back to this thing. I could have subtracted by hand this time. Of course, I might not have gotten the right answer. This comes out to be plus 2.96. Units. Or, no, it's all, you can always give it in Kelvin. They don't give it in degrees C, because there's not a delta T involved. In other words, when you're doing S, that's the definition, so you're always dividing by temperature in kelvins, you're not dividing by delta T.
It's not joules, Kelvin, mole.
What?
It's not joules, Kelvin, mole.
How many people said it's joules, Kelvin, mole? If you said that for that answer, I'd mark it wrong, because I'm desperate to find things wrong. So many 25s. There were so many 25s on that quiz. If I'd have found somebody who did something like that with the wrong units, I would take a point off. So don't forget to put the right units. Why isn't it mole? Why isn't it that? Because when I calculated this, this the other day. In other words, when you're doing those products minus reactants, you're always multiplying by the coefficients. You got rid of the moles. Okay? So when they give you the numbers in the tables, they're giving you for a mole of each of those substances. So this number here is for 1 mole of oxygen, okay? Or 1 mole of CO2. And this number is for 1 mole of oxygen. But when you put it into the products minus reactants, you're putting in the number of moles from the balanced equation. So when you calculate delta S for the reaction, and the same thing up here, this came out to be delta H sub F is kilojoules per mole, because here, it's the number you find in the table. If I wanted delta H for this reaction, it would be because when they give you the for enthalpies of formation or the free energy of formation, it's for 1 mole of that product material from the elements. Or if we're doing products minus reactants to calculate delta H for the reaction, you always have to put in the number of moles. So that's a good thing you asked. You might have had it wrong in the quiz or the exam, right? Like I said, I look for units. When everybody's getting 25s, I have to find somebody that didn't get a 25. So we can't give out 400 A's in a semester.